Hi students, welcome to another wonderful session. Today we are going to deal on the chapter Periodic Classification of Elements. You might have studied in your previous classes what is an element is. In chemistry, an element is a pure substance consisting of only atoms that all have the same number of protons in the atomic nuclei. Unlike chemical compounds, chemical elements cannot be broken down into simple substances by chemical means. So what does that mean? An element is the smallest type of thing that occur in a matter. So coming to classification, in this chapter we are going to mainly deal with the different types of classification of elements that the scientists have done from ancient times. So why classification is necessary? As we look in our daily life, we need classification as an important matter. For example, if we just go to a supermarket, we see things classified into different sections. If you are going to a section of soaps, there are a classification of bathing soaps, washing soaps, hand wash soaps, and different classification of themselves. So a classification of a particular thing is a basic idea or a basic necessity that we need to deal with. So that comes in case of elements also. So coming to elements, as of November 2016, there are 118 elements recognized by IUPAC, International Union of Pure and Applied Chemistry. The first 94 occur naturally on Earth, and the remaining 24 are synthetically elements produced in nuclear reactions. Since the ancient times, grouping elements was necessary because it was really hard and terrible to study each element's properties individually. That was really difficult for the scientists at those times. So scientists started classifying the elements which were known at that time based upon different properties, and they knew, and based upon different classifications were published. Therefore, classification of elements is an important thing. From ancient times, in the early 1870s, one of the scientists started classifying elements with the elements known at this time. His name was Johann Wolfgang Dobrino. His classification was called Dobrino's triads. In 1817, he arranged the elements with similar properties into groups. He just identified some groups having 3 elements. That groups were called triads. Triads means 3. These elements were arranged in the increasing order of their atomic masses in each triad. The classification which he made was the atomic mass of the middle element was roughly the average of the atomic mass of the other 2 elements, as you can see here. Just look at the picture. Lithium, sodium, potassium. If you look at the atomic mass of sodium, it is roughly the average of the masses of lithium and potassium. This is the same with the next 2 sections. This was Dobrino's triads. But there was a small problem. Dobrino could only identify these 3 triads. All the elements which were discovered at that time could not be classified into triads. This was a major limitation. So this was the first classification of elements that was made by Johann Wolfgang Dobrino. Next, this was another classification made by John Newlands. This was called Newlands Law of Octaves. John Newlands arranged the then known elements in the increasing order of atomic masses. He started with hydrogen and ended at thorium, that was the 56th element that was known at that time. He found a peculiar thing, that every 8th element had properties similar to that of first. This was exactly compared to the octaves found in music. Thus the name came Law of Octaves. As you can see in the picture, you can see Sa, Ri, Ga, Ma, Pa, Da, Ni, which means the element starting with hydrogen, the 8th element is fluorine, that has similar properties which is coming between hydrogen and fluorine. Similarly, this happened with these elements you can see in the picture. The properties of lithium and sodium were found to be the same. Sodium is the 8th element after lithium. Similarly, as you can see down, beryllium and magnesium resemble each other. So, in each cases, he observed this peculiar thing. Every first element showed a property similar to the eighth element coming after the first. This was called Newland's Law of Octaves. But there were also certain limitations with Newland's law. The first one was, it was only applicable up to calcium. After calcium, every eighth element didn't possess any properties to that of first. Newland assumed that only 56 elements existed on Earth, and he just thought that no more elements would be discovered in the future. But many were discovered in the future which couldn't be accommodated in the octaves. Next one was, Newland adjusted two elements in the same slot which doesn't have any similar properties with the element in the section. As you can see in the picture, there are certain cases where there are two elements coming in one section. Concluding, Newland's law of octaves worked well with only lighter elements. For harder elements, it didn't work. This was Newland's limitations. Next one is Mendelev's periodic table by Dmitry Ivanovich Mendeleev. This was the most perfect periodic table known at that time. Mendeleev was really cunning. He just arranged the elements on the basis of their fundamental property, atomic mass, and also on the similarity of chemical properties. At his time, there were 63 elements discovered. He examined the relationship between the atomic mass of elements and also their physical and chemical properties. Among chemical properties, the main thing he discovered or main thing he was concerned about was, the main thing he concentrated was how each element reacted with hydrogen and oxygen. The formula of the hydrates and the oxides formed by an element were treated as one of the basic property of an element. Thus, combining all these, he started to classify elements on the basis of atomic mass. He took 63 cards and on each card he wrote down the properties of one element. He sorted out the element with similar properties and pinned the cards on a wall. It was observed that most elements got a position on the periodic table and they were arranged in the order of increasing atomic masses. The peculiar thing or the most important thing he observed was there was a periodic recurrence of elements in the table which weren't seen on most previous periodic tables that were given by Newland or Dobrino. On this basis, Mendeleev formulated a periodic law which states that the properties of an element are the periodic function of their atomic masses. As you can see, this is Mendeleev's periodic table. You can see in different portions there are formulas of hydrides and oxides belonging to different elements written. And also there are rows and columns. In this Mendeleev's periodic table, a new terminology came. The vertical columns were called groups and the horizontal rows were called periods. So this was the Mendeleev's broad periodic table, which was a small successful thing at that time. But here there were merits and demerits. Let's first look into merits. The first merit was, it was easier to predict the properties of an element based upon its position. Second, there were some gaps which were left for undiscovered elements. Mendeleev just named by prefixing a Sanskrit name Eka to the name preceding the element in the same group. For example, scandium, gallium and germanium discovered later have properties similar to Eka boron, Eka aluminium and Eka silicon respectively. The noble gases, they are inert. They could be easily accommodated after their discovery without disturbing the current arrangement. This was a peculiar merit about the Mendeleev's periodic table. Next, demerits. As you see, there wasn't any fixed position for hydrogen. Also, you know about isotopes. Position of isotopes couldn't be explained. Also, there was some irregularity in the order at certain parts. Wrong order of atomic mass could not be explained. These three were the major demerits of Mendeleev's periodic table. But although coming through these demerits, Mendeleev's periodic table at that time was a huge success. Now we are coming to the modern periodic table that you can see in your textbook. It was developed by Henry Moseley. The modern periodic law was properties of elements are periodic function of their atomic number, not atomic masses. This was the key point used by Henry Moseley in developing the modern periodic table. As you can see in your textbook and here, this is the modern periodic table of elements. These much elements are here. We have different categories, differently considered as different categories and different blocks, and elements are very well classified. Elements in the same group has same valence electrons, same number of electrons. Elements in the same period has same number of shells, and electrons being added by one as the atomic number increases. Elements were classified into different blocks based on their positions. The main thing was hydrogen has a proper position here. The problem of accommodating isotopes is solved since we are not arranging the elements on the basis of atomic mass but only on the basis of atomic number. So the problem of arranging or fixing the position of isotopes is solved. So these were the key points that we can see in the modern periodic table. Finally, the trends in a periodic table. First one, valency. As you have studied in your previous classes, the valency is the combining capacity of an element in forming a compound. Valency can either be gaining of electrons or losing of electrons. Purely with an example, carbon has 4 valence electrons in its valence shell. As you all know, to be stable, it must complete an octet form, which means carbon needs 4 more additional electrons to form 8 electrons. Or to obtain a stable configuration, it must have at least 0 electrons in its valence shell or 8 electrons in its valence shell. So in this case, carbon can either gain 4 electrons or lose 4 electrons. So the valency of carbon is 4. So this is valency. In a periodic table, as you just saw, the elements in the same group have same valency. Why? Because elements in the same group has same number of valence electrons and also their gaining or losing capacity is same, that results in the same valency. Next one, atomic size. Down the group, atomic size increases. Across a period, atomic size decreases. This is because, as you just observed in the periodic table, down the group, the number of shells increases, which means the last electron is very much far away from the nucleus. As the shell size increases, as the number of shell increases, the distance also increases, which increase the atomic size. If the first shell is this much, the next shell is this much, which means the size increases. Across a period, atomic size decreases. This is due to nuclear charge attraction. As you all know, one electron is added by increasing the atomic number by 1, which means extra electron is being added. This increases the attraction between the total electrons and the nucleus, thereby shrinking the atomic size. So the atomic size decreases as we go across a period. Next is metallic and non-metallic properties. Down a group, metallic character increases. Across a period, metallic character decreases. This is because down a group, mainly in the metal side, which means left extreme side, metals can easily lose electrons. While going down a group, the electron is very far from the nucleus, from which electrons can be easily lost. This gives the element a metallic character. So, down a group, metallic character increases. Across a period, metallic character decreases, because across a period, one electron is being added by increasing atomic number by 1, and hence the nuclear force of attraction increases, thereby reducing the chance of losing an electron compared to the previous state. So, non-metallic character increases as we go across a period, which means metallic character decreases. Metals easily lose electrons and they are electropositive. Across a period, electropositive character decreases and elements become electronegative.